So when we talk about free vibrations for underdamped system, so we know that your solution is going to be AE to the power of something. So that means is an oscillation that decays, whose amplifier decays exponentially over time. And then these A is our amplitude, 5 is our phase lag, and then we set that A and 5, they depend on your initial conditions. But there's one thing I forgot to emphasize, which is this 5. I think it's also wrong in the textbook. So if you look at the plot of a tangent 5, so that means when you need to calculate the invert tangent, so actually there were two solutions from 0 to 2 pi. So that means in one complete cycle, you can actually find two solutions. So by default, if you use MATLAB, if you use the A tangent function in MATLAB, it only gives you the phi1, which is the first solution, because this arctangent function gives you a solution in this range. So that's what the arctangent is going to give you. So these arctangent works whenever your x naught is greater than 0, whenever you have a positive initial displacement. But then, if your x naught is smaller than 0, then it's actually wrong, because that 5, your phi2 is actually the solution you want. So that's why if you use these equations to calculate your phi, always remember arctangent is going to give you phi1. There is another potential solution, which is phi1 plus pi. You have to pick one out of these two. So there is only only one of these is correct. So how did you do it? So this is the equation you want to use. So for example, you can simply use the first one. If your x naught is positive, that means your phi should be between 0 to pi, right? If x naught is positive, your phi should be pi to 2 pi if your x naught is negative. You can judge which phi is correct just based on the initial displacement, and then you can also judge which one is correct based on your initial velocity. So just one more step when you calculate the free vibration. You're going to see these in the quiz 5. So that's for one of the corrections. Oh, one more thing. I posted a tentative final project on Blackboard. So please make sure you quickly review it. And there are two options, as I mentioned before. It's either a group project or an individual project. So I can see the merits and drawbacks for each option. So I initiated a survey on Blackboard. So the deadline for that survey is this Friday by 5 p.m. And then based on your input, I'm going to post the final project by the end of this Sunday. All right. So make sure you provide your comments to that survey. All right. So in 2 days, we're going to have exam number 3. Well, in this class, I'm going to emphasize a lot of examples. So some of you has already uploaded your solution for quiz 5. Actually, I post my solutions one day after I post the quiz 5. And so something I can assure you is that quiz 5 is the upper limit for in terms of difficulty for exam number 3. So that means your exam 3 won't be harder than this. So make sure if you understand how to solve all of these questions, then I think you're going to get 100 points in exam 3. So let's go over these problems one by one. Let's create all right, so see how to do it. Let's insert another page. That's weird. Quiz number 5. All right. So I'm gonna review all these questions right now. So let me know if you have any questions. You can just raise your hand, or just type in the chat. And also, if you still have, so try to work on these even after class. If you still have questions, you can participate in the office hour tomorrow morning from 10:30 to 11:30. All right. So let me highlight something. So for these exams, the backbone or the most important thing you have to understand is called superposition, because we learned a lot of different kind of excitations. We learned impulse excitation, periodic, arbitrary, step input, square waves, a lot of different things. But then the backbone of these force excitation is called superposition. That means whenever you have a force excitation applied to a system, you should try to cut that system into small pieces. I call them building blocks or subsystems. So in the end of last lecture, I try to create a table for you. So if you don't remember, I'm going to post it up again. So that's the table I provide. I already posted this on Blackboard. So in this table, I summarize basic building blocks or the basic subsystems you might need to use for exam 3. So starting from the simplest one, which is free vibration, harmonic excitation, impulse, stepped input, arbitrary force, periodic input, and some excitations that can be done through inverse Laplace transform. So first of all, you have to understand those like basic solutions. Once you understand those basic solutions, then you're going to see all these quiz problems. They just like a superposition of those basic inputs. All right. So let's look at question number 1. Let me try to copy this. It's still there. Interesting. All right, let me start a new one. All right, so that's the first questions we're going to deal with. So we have a system, it's a linear, and it's a linear system, underdamped, and is a first order, and is a stable system. So first of all, we have one impulse, number 1, and then there's another impulse, number 2, and then we have initial condition. So 1, 2, and 3. Then you can see there are 3 basic excitations. So that means we need 3 subsystems. So that's why whenever you see a problem like that, first you need to determine how many subsystems you have. You have subsystem 1, 2, and 3. And always remember the subsystem 1 is for initial condition. So even your system is initially at rest or the initial conditions are 0, I still recommend you to put initial conditions as subsystem number 1. In that case, you won't forget anything. All right. So in this case, you have initial condition x0, and remember, this initial condition is at x0 minus. That's before the impulse is applied. And then you have your V0 minus equal to 0. And then what's the solution for these type of excitation? So that's just a free vibration of under certain initial displacement. As I said before, the solution here is A E minus zeta omega n t psi omega d t plus phi. We just mentioned these. So this is actually in the table I already gave you. So the A is a function of x0 and v0. You can just go to lecture 3 to find the expression for A and phi. All right, so that's your solution. So the second system is impulse number 1. Your impulse number 1 is actually 2 times a unit impulse. So in this case, you have to go to lecture 11. That's where we talk about impulse excitations. And then if you remember, the response for that system is F hat times small ht, right? So your F hat is the amplitude of your impulse excitation. So in this case, your amplitude is 2. So your F hat is 2 times ht. And then what is ht? ht is in the lecture 11, is 1 over m omega d e minus zeta omega nt psi omega dt. So as I mentioned before, in the class, if you think ht is too long to write it down. Yep.
If I'm not mistaken, I thought that was only for zero condition ht values.
That's actually a good question. I'm not sure if I've been clear on that or not. So when we talk about impulse excitation, let's say we have an impulse delta t, right? So how we solve this system is we convert it to initial conditions, right? So we're according to, so F times delta t equals to m times delta v. That's the impulse momentum theorem. So we can convert this impulse to a initial velocity. So that means your v naught is F hat over m, right? But then just remember that this v naught is not the same v naught we mentioned in subsystem number 1. This is actually v naught plus. So that means, well, so this equation is true even your system is not initially at rest, or h naught or v naught. So this expression is always true no matter what kind of initial conditions you get. You might feel a little bit weird.
Right,
because
so that condition makes sense. It's the equation right below it with the ht equaling to 1 over m omega d times e to the, so forth and so on. But
so what I'm trying to say is, let me solve these, and then let's come back to solve these initial condition question. Okay, I think it makes more sense to explain it that way. So so that's for the second system. For this third system, you have impulse number 2. So impulse number 2 is a unit impulse delayed by 1 second. So the solution would be similar. So it's going to be F hat, and then the time dependent part, you need to delay it by 1 second as well. So that means 1 second delay in excitation means 1 second delay in response. So in this case, your F hat, because it's a unit impulse, so this F hat is 1. So you directly have ht minus 1. And then remember, your impulse number 2 comes in only after time is greater or equal than 1 second. So that means this happens, or this x3 exists, only t is greater or equal to 1 second. So the other way to write it down is you can use a Heaviside equation, use a big phi, t minus 1. So that can represent this type of thing. So eventually your xt is just x1t plus x2t plus s3t. All right. So I think the question related to the initial conditions is, if you plug t equal to 0 into xt solution we got, so these xt equal to 0 won't be the same as x0 minus. And then your vt equal to 0 won't be the same as v 0 minus. Because right now, if you look at the initial condition here, it has both x naught minus and x naught plus in it. Okay, so that's the weird part. So previously, I think some of you might try to check your solutions by plugging the initial conditions back to see if that matches with the initial conditions provided. But for these kind of impulse excitation, you won't be able to do that because the initial condition is because of the 0 positive and 0 minus thing might not be the same. So does that make sense? I think your question is
I think it kind of does. I was just looking at lecture 11 slide 3, and it just shows that x at 0 is equal to 0, and then x dot at 0 equals 0 as well for those equations for h of t. But I could just be wrong there. You know, that's where I'm confused.
Lecture 11, which one? Which slide?
3.
Slide number 3. All right. Oh yeah. So, God, I got you what you're saying. So that's actually, you can treat these as an example. So x naught equals to 0, x naught dot equal to 0. Yes, that's because your subsystem 2 here. Let's go back to the quiz. So here, let me use a different color. So here you have initial conditions, and then your ft will be 0. Once you want to consider your force, then all your initial conditions are 0. That's how you divide your subsystems.
Okay, and so we could use the HT equations from those.
Yes, okay. Correct.
All right.
So,
go ahead.
Go ahead. Oh, yes, I'm not sure if you take any like electric circuit class. So if you have multiple, like if you have a voltage source, you have a current source to drive the same electric load. So what you can do is you can actually, I forget what's the name of that theorem, but you can actually divide these into 2 circuits. So the first one is I over R. That might not be a good example. Plus V over R. That's also called superposition. You can see here, you have 2 sources. One source is voltage, the other source is a current source. So that means when you do superposition or when you want to cut your system into subsystems, you just focus on the first subsystem. Like for example, that's your first subsystem is a voltage input. If you focus on the first subsystem, then you set the second subsystem as 0. So that means when current is 0, then you have an open loop.
Okay.
And then, so that's your subsystem 1. And then for your subsystem number 2, you leave your current source there, but then the other source have to be 0. So that's why voltage is 0. That means it's short connected. So here in this case, you have force number 1. You have a force, that's number 2. You have a second force, number 3. You have initial condition number 1. So when you look at system number 1, your number 2 and number 3 should be 0. So that becomes a free vibration. If you focus on number 2, 1, and 3 are 0. So no initial conditions, no force, no second impulse. Make sense?
That makes sense. So it's much more like a it's like it's a superposition
Yes.
sort of problem. Okay.
Yes. I need to figure out what's the gosh, I learned all these electric circuit theory in Chinese, so I forget. I don't know what's the name of that.
This actually makes perfect sense. That clears up a lot of it, because when I was taking the quiz and I went and looked at your solutions after I'd finished the problem, I was like, you didn't show the use of the impulse equations. And then I was like, okay, maybe it's just because since the initial conditions are not 0, but that makes more sense now.
Okay, so I think Tarek also asked a very good question. How to write these Heaviside function. So there are way. So Heaviside function is just a way to help you to merge your piecewise functions into one expression. So let me write it out. So for example, in this problem, you can actually the natural way to write it out is something like this. So this is time greater than 0, smaller than 1. This is time greater than 1 second. If you provide a solution like this, I'm completely fine with it. So the Heaviside, let me see. That function is defined in such a way that is 0 when t is smaller than 0, when it's 1 when t is greater equals to 0. So you can also add time delay to this equation. If you add a time delay of tau, then it's still 0 to 1, but then everything is delayed by tau. So t is smaller than tau, and then t is greater or equal than tau. All right, so let's look at this expression. How can we use the Heaviside equation to simplify this? The first part, x1 plus x2, they always exist, no matter where your t is. But then if you look at the second part, your x3, it only exists when t is greater than 1. So that means you can also write it as x1 t plus x2 t. You don't have to do anything. If you want, you can actually add a 0 there, right? Because all the input happens at time equal to 0, but in this class, you can ignore that 0. But then for the second part, it only exists, oops, I shouldn't 0, it should be 5t. The second one is 5t minus 1. So if you want to write your solutions using Heaviside, so that's your solution. So either one, so number A or number B, so both of them are correct. Make sense? Actually, if you want to write it out, if you want to expand the first one, it's actually 0 when time is smaller than 0. So that's why we have to add the first 5t in front. But because in mechanical systems, we usually talk about positive time. So you don't have to leave it there. But in electric systems, you might want to keep it there. Does that answer your question, Terry? All right, cool. So yeah, try to solve these after class. Let me know if you have any questions. So the second one, let me copy and paste. Oops. All right. So the second question, so we use inverse Laplace transform to solve the following two equations. As you can see here, the two systems, they are identical. But the only difference is you have different initial conditions. So if you want to use subsystem to solve these two, that means for the second equation, you actually have one more subsystem. So you're going to expect different solutions for sure. Let's look at how to do it. So first of all, let's do Laplace transform. Oops, use a different color. You have 4 double x dot plus 6x equals to 2t. And then you have your initial velocity, initial position. So then you need to go to which lecture? Done. Let me put it up. I think it's lecture 13, I believe. Yes, you need to go to lecture 13. There is an equation there. It tells you how to do Laplace transform. So your x dot after Laplace transform is s squared xs minus s x naught minus v naught. Your x single dot is s xs minus x naught. Right. And your x is directly xs. And then you have to do Laplace transform for your force expression as well. So your ft is 2 times t. So that's why you have to be really familiar with your table. So then you need to go back to the Laplace transform table. So that means on these 4 time-dependent function column, in this column, you need to create a 2 times t function. Where can you find it? It's not that obvious, but it's definitely in this. So you need to focus on number 10. So when n equals to 2, you got t 2 minus 1 over 2 minus 1 factorial. So it's t directly. So then when n is 1, the Laplace transform is 1 over s squared. So this is from time, a slope function. We actually call this a slope function. That's t, that's ft. It increases linearly with respect to time. A slope function is 1 over s squared. And then you have it's not a unit slope, it's actually 2 times t. So you just put a constant t, 2 in front. So that means your 2t just becomes 2 over s squared. If you don't remember that, if you don't remember how to find that thing in the Laplace transform table, you can always use Laplace function in MATLAB that can help you directly convert 2t to something. I think I already have these in the lectures 13 MATLAB examples. Make sure you want to check it out. If you don't want to search the table, directly use Laplace. Is able to convert these Laplace transformation for you. All right. So we have everything, and we just need to plug things back in. So the first part, A, all the initial conditions are 0. That's really nice. You can forget all about these underlying terms. So let's put things inside. You have 4s squared xs plus s xs plus 16xs equal to 2s squared. And then because we want to solve for xt, so in order to get xt, you first want to find the solution in s domain. So that's why your x, you just collect terms, collect all the xs, and move all the other stuff on the other side of the equation, right? So that's the solution in s domain. And then the last step is to convert it to time domain. So you just need to use inverse Laplace. So if you use MATLAB, so this I Laplace function is what you need to use. So I Laplace, to pass exam 3, that's something you definitely want to learn. Laplace, well, it's highly suggested because it's able to greatly simplify your solution. All right. So that's for question number 2. For part B, because the initial conditions are no longer 0, you just keep your initial conditions there. You have -1 and 1. So you just plug everything back in. Your x s squared. And because your x naught is -1, so it becomes positive s minus 1. Yes, it's positive 1. So plus x s s and that's -1 and +1. And then the last one is 16xs. So equals to 2 over s squared. So let me underline these. That's the Laplace transform for 4x double dot. That's the Laplace transform for x dot. That's for 16x, right? Just pay attention. Don't make calculation mistakes. So plug these back in. And then as I said, so you need to find out what the x solution in S domain. So all the other terms needs to be moved to the other side. So you have these constant terms, -4s and +3, and then divided by the coefficients, right? And then you just do Laplace for whatever on top of these. So this procedure, I actually provide you a very nice MATLAB code in lecture 13. So that one allows you to directly solve this ODE with one click. If you want to make it really easy, you might want to check that MATLAB. All right. So Q2 inverse and Laplace and direct Laplace transform. I think that's straightforward. I'm expecting a lot of the calculation errors, so please pay attention and try to prove I'm wrong. Okay. So any questions for Laplace? So if no questions, I would like to spend some time on Q3. Q3 is a very typical question for exam 3. So in Q1, let's go back to Q1. Once you see this problem, you can directly see where the subsystems are. Okay, there were 2 impulses, 1 initial condition. We should have 3. Subsystems. But then in this case, all right. So how many subsystems we have? Well, actually, a lot of you, when you saw something like this, okay, this force looks like an arbitrary force. Then you want to use xt equals to 0 to t f tau ht minus tau d tau. So in previous exams, whenever you see something like this, a lot of students choose to use the convolution integral to solve this problem. Actually, that's doable, that's feasible, but you might not be able to complete the problem within the time window I gave you. Yes, you're correct. This integration is not straightforward because your f tau, it actually has 3 different expressions in different time windows. So that means you have to do the integration for time is smaller than 1. So in this case, your ft is directly t. And then when it's greater than 1, smaller than 2, then it's actually minus t plus 2. And then eventually is 0. It's doable, but you have to do this integration piecewise, like step by step. So you need to cut your ft into 3 steps, and then your integration has to be done 3 times. So that's not ideal. So the other way to do it is actually using superposition. So let's look at here. So you have a square wave. All right. So subsystem number 1 is initial conditions. Always in initial conditions. In this case, all the initial conditions are 0. So that's why the solution for these free vibration is just 0. Your system is not moving at all due to the initial condition. Then what is your subsystem number 2? Well, it's definitely not. So let's try one potential approach. Let's say your number 1, F1T is something like this. It's just a slope function, right? That is 1 second, that is 1. So your subsystem number 2, or F1, is directly a slope. That means for this subsystem, what we have? So we have x double dot 4, x dot plus 16x equals to t, right? That's your subsystem number 2. We already solved these using a Laplace transform. If you remember, the only difference is the slope is not 2, it's actually 1. So you can directly solve these using Laplace transform. You can use Laplace and I Laplace to solve this. I'm not going to repeat these. Let's directly write it as x2t. So let's say you can use I Laplace to find that. Then the second equation is t 0. I think that's the challenging part, the equation number 3, the subsystem number 3. So you want to create a function. That function starts at time equal to 1 and with a slope of -2. I'm not sure if that's clear to you. So the function of this subsystem number 2 is, let's recall what we have initially. We have something like this. 0, 1, and 2, that's 1. The function for subsystem number 3, or F2, is we want, so without this subsystem, your step function just keeps going. We want to manually add another subsystem to bring it down. So if we only add a slope of -1, then we bring it flat. From there, you have to add a -1 slope. And then from flat to -1, you need another -1 slope. So that's why in order to bring these projection all the way back to the force we want, the third subsystem we need to create has to have a slope of -2, right? So that means for this system, you have x double dot x dot plus 16x equals to -2 t minus 1. That's your subsystem number 3. So if you look at this subsystem, you have -2, which is a slope, times t minus 1. That means this slope function is delayed by 1 second. As you can see here, it's not starting at 0. It's starting at time equal to 1. So everything is delayed by 1 second. And then you can use I Laplace or Laplace transform to find the solution x3t. How to find these using Laplace? It's just the same thing, right? Because your initial conditions are 0. That's why when we, similar to question number 1, when we focus on the force, all the other excitations are 0, including initial conditions. So if you pick to focus on the force excitation, initial conditions are always 0. So you can find the x3t using Laplace. And then remember, we need to force subsystem. So these subsystem, it should start at time equal to 2. So what we need to do, so without any further subsistence, let's see. So that system is going to keep going forever, right? But then we need to bring it flat again. So how to bring it flat? We just use a +1 slope to bring it flat. So that means your subsystem number 4, it should be +1. That slope is k is +1. And then if you want to write it out, your subsystem number 4 is something like this. It's positive slope with a time delay of 2 seconds, right? And then initial conditions are all 0. because we focus on force excitation, no initial conditions. And then you can use Euler plus to find the xt. And remember, one thing you have to remember is these subsystem 3, it only exists when time is greater than 1 second. And then your subsystem number 4 exists when time is greater than 2 seconds, right? The other, so if you knows better, if you know, really understand what's the time, what's the meaning of time delay, you can actually see that your subsystem number 2 and subsystem number 4, they're actually identical, just with 2 seconds of time delay. So that means if you want, your x4t can be written as x2t with 2 seconds of time delay. So you don't even have to run the initial Euler plus again for these subsystem 4. But it happens when time is greater than 2 seconds. So, and then after that, no more subsystems, because ft equal to 0 can keep going. That's what we have. And then you have 1, 2, 3, 4 subsystems. And then your final solution is the sum of all these solutions. And then you need a I minus 1. So that's the final solution. It feels really complicated, but compared to this convolution integral, it's actually much easier. So that's actually a very complicated question, because I came up with this quiz 5 right 1 hour after our lectures. So in the exam 3, I might not give you something like that. So I think that's too complicated for exam. I will give you something, I think last year, what I give the students is something like this. And then initial condition. That's the exam 3 from last year. That's your ft, that's your t. Try to think about it.
That one would just be just like your 2 conditions. You'd have your initial, or sorry, you have 3 subsystems, right? It'd be initial, then you have f equal to 1, and then f equal to 2, right?
Yes, I think you fell directly into the trap I gave you.
Yeah, but the trap there would be that if you did the 2, then it technically brings the magnitude up to 3, right? So it'd be like
no, actually, it's actually a subsystem like this. That's 1. That's also 1.
Yeah, exactly. And then you'd have a heavy side, because if you accidentally did 2, it'd bring up the magnitude to 3 on the overall.
Exactly. So the most common mistakes I saw last year is a lot of people using 2 over there, because they thought, okay, that's amplitude number 2. But remember, part of the amplitude is inherited from the first subsystem. So your first subsystem is something like this. So that's your first subsystem. And then your superposition only compensates for the difference. So that's why your second subsystem is actually only the red part. Make sense?
Yeah, that's pretty crystal clear.
Yeah, so if you understand that, that's super easy. But last year, what I saw is I think 80% of the class is getting 2 as the amplitude. It's like a cake. So each subsystem contributes for 1 layer. All right. I think in exam 2, this question is going to be the most challenging one, because you need to be able to find the subsystems. All right. Okay, so what is Q4? So Q4 is for Fourier series. Oops. You have a periodic function you want to find the Fourier series of these periodic functions. So what does that mean? So what is the Fourier series? So if you have a periodic signal, if ft is periodic, that means you can write your ft into a summation of cosines and sines. So that's your an cosine n omega dt plus bn sine n omega dt. That's called Fourier series. So the equations can be found on lecture 12, slide 4. So first of all, you need to understand what is omega t. So omega t is 2 pi over t. The t is the period of your period of ft. So sometimes we call this omega t the fundamental frequency. And then n omega t, that's the higher harmonics or harmonics. If n is 2, we say that's for a second harmonic, third harmonic, and keeps going, nth harmonic. So that means your n has to be integers, because you can only have like a certain number of harmonics. That's for periodic signal. If it's not periodic, then you want to use Fourier series, then it gives you Fourier transform. Then your n is no longer discretized. It's actually continuous. Then there's something different. All right, so that's your omega t, that's your n omega t, and then all the other things we need to find is a naught, a n, and bn. So I don't want to rewrite all the equations again. You can find it on lecture 12 and on slide 4. It's a lot of calculation, trust me. So I already provide you actually 2 homework solutions. You might want to check out lecture 12, the solution of 2 homeworks. Make sure you understand those MATLAB codes. If you know how to run those MATLAB codes, that can save you hours in solving this Fourier series problem, because that MATLAB code is able to find a naught, a n, bn automatic for you. Otherwise, you have to do manual integration. So here, I'm going to show you how to do manual integration. Your a naught is from 2 divided by t, 0t, and ft dt. Your ft is actually a piecewise equation. So that's why you have to do an integration from 0 to 1 second. In that time period is just t dt. In the second part, it's from 1 to 2 seconds. You have minus t plus 2 dt, right? And then you have to calculate this integration and then find your a naught. So a naught is usually easy. Your an is 2 over t integration from 0 to t. And this ft times cosine n omega dt. And then again, you have to do these piecewisely. So from 0 to 1, ft. And remember, in that case, your ft is just t cosine n omega n t. Plus, in the second piece, it's from 1 to 2. That's 2 minus t cosine n omega t dt, right? You can see how complicated that integration could be. So All right, so then if you know how to use, oh, it's just 2t. No, it's minus t plus 2 because the slope is -1.
So
If it's minus,
I'm just curious because before the slope was -2 because we had to go from a positive slope, then to flat, then to negative.
oh, I see the confusion there. Well, this is different. This is different. So this Q4 is actually different from Q3.
Okay.
We're not recreating that sawtooth or triangular tooth using subsystems. We're directly doing Laplace Fourier transform or Fourier series. So whatever we saw on question 3 no longer applies.
Okay, thanks.
You just directly use the FT expression. So, yep. So then make sure check my lecture 12 MATLAB Go that helps you to complete these all analytically in MATLAB Live Script. Otherwise, it's going to be a huge pain. You have to search integral table, find these standard formats, and then do it manually. So it's a pain. So try to learn MATLAB over there. And then Bn, what is Bn? So as I said, there are a few ways to simplify this. So one thing, I think one thing I forgot to emphasize is here. So the other difference compared to these FT to question number 3 is these triangular wave exists before time equal to 0. Because as a periodic signal, it starts from negative infinite time to positive infinite of time. But if you look at there, it only exists off time to equal to 0. So that's why you can cut it into small subsystems. But then assuming that you have a lot of things going on in the negative time domain, then there's no way you can write it as a few subsystems. It's actually an infinite number of subsystems. Make sense? Yeah, personally, I still think for these force excitation, what's happening before time equal to 0 actually matters a lot. So sometimes it can be confusing. Even you see the same triangular wave, but in this case, this triangular wave happens before time equal to 0 and then keeps going. It's going to be different from single triangular wave. All right. The other property I mentioned is if you have an even function, that means your function is symmetric with respect to y-axis. That means all your Bn should be 0. If it's an odd function, that means if you rotate your function around the origin by 180 degrees, you get a perfect overlap. So that's the odd function. If it's odd function, then all the A values are 0. So that's a good way to check your Fourier series coefficients. For example, if in this case you get Bn not equal to 0, that means something is wrong in your calculation. All right. So that's how you find An, Bn, and A naught. Eventually, your Fourier series Ft is just A naught. What is the solution over there? Let me just copy. Yep. That's the solution. Oops. Oh gosh, doesn't allow me to copy, but anyway, you get the point. So eventually, Ft is A naught divided by 2 plus summation of n equals to 1 all the way to infinite, and then An cosine n omega t. So all the sine terms become 0. So part number 5. So when we apply these sawtooth periodic or sawtooth to a second order system, how can we solve this? So when I assign these to students, a lot of you actually trying to use ODE 45. Actually, in this case, ODE 45 is not easy, because assuming that you want to use ODE 45, so then your FT becomes crazy. Your FT would be T is greater than 1 minus T plus 2. T is smaller than 2, greater than 1. And then it's going to be T minus 3. T is greater than 2, smaller than 3. And then minus T plus 4. 3, T minus 4. And then it keeps going. So if you want to use ODE 45, I think it's still doable. But then when you create your FT, it's going to be a huge pain. You have to divide it by piecewise, like section by section. And then you're going to get an infinite number of sections. There is some kind of like a patterns there. You might be able to do it, but it's just not convenient. All right, so if you have periodic signal, the best way to do it is actually using Fourier series. So let's post it in here. Oops. I'll paste it. Copy. Paste. All right. So let's look at this system. How many subsystems we have? Always you have a subsystem number 1, which is your initial condition. They are all 0, so that's why it's A, E, minus zeta omega n t sine omega d t plus 5. And then these A and 5, they're determined by initial conditions. But then this is very different from the impulse. If you look at my solutions online, you won't be able to determine these A and 5 right now. That's different from impulse. If you don't have an impulse in your system, you won't be able to see sharp change in your initial condition. So that means if your final solution is your xt, that means your x naught have to be equal to x naught, or have to, in this case, have to be 0. So you have to solve all these subsystems first, and then plug time equal to 0 back into the equation. And then in the end, you can solve A and 5. It's very different from what we saw before. It's different from the equation of question number 1. That might not be really clear, but hopefully you understand. Because this FT is not a sharp change. That's because FT is not a impulse or sharp change. So that means no sharp changes in, I should say, at time equal to 0. So that means your system is going to be very smooth. So if your system is like time equals here, that's your xt, or that's your t, that's your vt. At time equals 0, you're going to see a continuous or differentiable point at time equal to 0. Because there is no impulse. Only impulse can create sharp jump in your response. So if there is no impulse, that means no sharp jump at time equal to 0. So that means these initial conditions has to be satisfied by xt. That's different from the very first question. as I mentioned here, the actual initial conditions doesn't have to be satisfied at time equal to 0 because your impulse is going to create a sharp change. All right, so let's keep going. So you have subsystem number 1, A and 5, they're to be determined. Your subsystem number 2. So then you have to replace your FT by whatever Fourier series we got. And we said, so here I didn't mention how much, oh, I did mention that. Let's truncate your Fourier series at n equal to 10. That means we don't have to go all the way to infinite. Let's stop at n equal to 10. Then how many subsystems do you have? You have the static input A0. You have subsystem number 3 all the way to 22. Actually, because we have no cosines, it's actually only number 3 to number 12. This number 3 is n equal to 1, n equal to 2, all the way to n equal to 10, right? So for each n numbers, you have a harmonic excitation. So you have to go to lecture 7 or 8 to find the solution. That's the second harmonic excitation, nth harmonic excitation. So you're going to have x3, x4, x5, all the way to x12, right? So for the second system, your x2 is just A0 over 2 divided by k. Your k is 16. A special case is for these static input, it just create a static deflection. So you're going to get a stage like a static response. Eventually, your solution is just x1 plus x2 plus all the way to x12. So that's why for this kind of problem, you want to use MATLAB. Otherwise, you have to do this all manually. And then remember the A and the 5 in your x1, they're still to be determined. They're still unknowns. What you need to do is you need to plug in x equal to naught equal to x naught, v t equals to naught equal to v naught. I should say. Then you still have 2 equations from your initial conditions, and from the 2 equations, you can get A and 5. All right. Yes, it's a lot of things to digest. I'm gonna post. Let me stop recording.